Hello, everybody. I'm going to try to do a little video here for a lecture on speeds and feeds. The speeds and feeds section within the semester-long notes is pretty self-explanatory. But let me share my screen. Here's the semester-long notes. Okay. And where we start, it's right after the S. You guys have just been working on the S, or should be working on the S, in order to determine definition of profile. And what is a definition of profile? But down in this section here, determining power requirements, notice I put a square around the important variables and their formulas for calculating RPM and feed rate. Okay. Now, realizing that when we're calculating RPM and feed rate for a mill, that is not too far off of doing it for a lathe and turning, or for drilling for that matter. All right. So the RPM formula is 3.82, which is a constant. And that constant comes from two numbers that don't change in a fraction form. And that is 12 over pi. All right. When you divide 12 by pi, you come out to 3.82. Now, a lot of people just use a 4. All right. They just rounded up to 4 because it's easier to remember. But multiplying 3.82 times the quantity of VC over D. All right. Forget the subscript. All right. The subscript in turning, milling, and drilling changes. All right. Well, the D is diameter. So in turning, it's the diameter of the stock. In milling, it's the diameter of the tool. All right. And in drilling, it's the diameter of the drill. So they use this the subscript of T, the subscript of M, and the subscript of D, simply to let you know that you're talking about turning, you're talking about milling, you're talking about drilling. But we take it one step further. We take it one step further for the understanding that what diameter are they talking about? So right now we've been focused on milling applications, so we'll stick with milling applications. Okay. So when you're calculating RPM, we need to know VC, and we need to know the diameter of our tool. All right. The diameter of our tool is important because a larger diameter has a larger circumference. All right. So at any given RPM, a larger tool is going to be covering more surface area. Okay. And VC equals the units of measure of SFPM, surface feet per minute. Okay, so now I'm going to switch my screen and try to draw on this whiteboard that they have here that I could try. All right, so I talked about V sub C, the surface feet per minute. So if I was to draw a circle here, and it's that big, and then I'm to draw another circle, which is that big, okay? Now, when the small circle spins, it's going to only roll that long, okay? When the larger circle spins, it is going to cover that much ground. Of course, my sizes are only artistic representations right now. I really don't know how long this line is I drew. All right, but that is the concept of surface feet per minute. So every time the tool turns, it covers a certain amount of surface feet. All right, a larger tool will cover more surface feet than a smaller tool because the circumference is greater. Okay. All right, so that is the concept of cutter velocity. All right, cutter's velocity is surface feet per minute. So feet per minute, all right? And it's not to get confused with the second thing we need to calculate, which is feed rate, all right? So spinning the tool has a velocity, and it's measured in feet per minute. That's what V sub C is measured in, feet per minute. And we use it to calculate the required RPM, all right? Now we have to control RPM because certain materials and tool bits, the combination between tool bit and material, it can only withstand so much rubbing. And the reason being is it can only withstand so much heat. All right. So there is a volume of books out there that creates the optimum V sub C based upon how much heat buildup that a tool can withstand. All right. So then we turn our attention to our feed rate. Feed rate, okay, lower F sub M, or the M stands for minutes, all right, feed rate per minute, okay, is the feed per tooth, F sub T, times N, the number of cutting edges of your tool, times RPM. So you can see that it's necessary to solve for RPM first, then you plug that answer into your feed rate per minute. And it's very easy to do, all right? You got to know what tool you're using to know how many cutting edges you have. So you'll solve for RPM, you have it. You know what cutter you're using. It's either going to be a 2-flute tool, a 4-flute tool, or a 6-flute tool, something like that. Number of cutting edges is the key. And then the feed per tooth. Now, feed per tooth is one of those things that we pull from a chart again because of the complexity in calculating it. So let me go back to my whiteboard. I come back to the whiteboard here. And let me try to draw now. This is going to be fun. The bottom of a tool. All right. So if I was to take a look at the bottom of a tool, you would see flutes. This being a flute and this being a flute. Flutes are where the chips build up when the end mill is cutting. All right. We have to control how much material each tooth, cutting edge of the machine, is taking off as the cutter is progressing through the part because of the volume of material that is leaving the part. This flute can only fit so much material, all right? You can only put, 8 ounces of water in an 8-ounce cup, okay? And tool size determines the size of the flute. So of course, a larger tool could take more material, all right? So we need to determine chip load based upon the size of the tool. Okay, and the way we do this, the way we find V sub C and F sub T, the feed per tooth, is to use charts. Charts like this. These are 2 pages from the volume of books that I have that does give us a V sub C and F sub T. Now you can find them in the machinist handbook. You can find them on the inserts that you buy. You can find them on the end mills that you buy from a company. That will give you some pretty good estimates on what you can do. All right, but when you don't have that type of resources, you're not buying a new tool for a job. You're pulling one from a tool crib, or you're just picking up a tool around the shop and you need to make a cut and you don't know where to start. Well, this is how you start. Okay. So I have 2 different sheets here that I copied from the supplemental material that I have. It's called end milling slotting. And the next one is end milling peripheral. Okay, so we need to be able to now determine whether we have a peripheral cut or whether we have a slotting cut. All right, that's the biggie. That's what's going to get us started. Knowing if you got a slotting cut or knowing if you have a peripheral cut. So going back to the whiteboard, okay, we could say if the R radius let's see, now I'm confusing myself trying to learn how to use this whiteboard to type things out for you. If the radial depth of cut is greater than or equal to, is greater than or equal to the radius of cutter, then you have a slotting cut. All right. So it's an if then else statement. And I usually, let me try to just draw it for you. I like to draw it like this on the board when we're in class. If R sub D is greater than or equal to radius then, I use my 3 dots, then slotting better close that O. Okay. The if statement, the else statement, else is the periph. All right. I won't be doing that much more. Okay. Clear that. All right. So now we need to know what is R sub D and what is the other one? What is A sub D? All right. So take this to be an end mill. All right. A side view of an end mill. Okay. All right. R, the radial depth of cut, is the distance that the cutter is in across its radius. The other type of cut we can have is A sub D, and that is the axial depth of cut. And that is the depth of cut that we can be in along its axis. Okay. All right. So looking at the end of this, the stock, if I was to draw a piece of stock now, you could view that an end mill is both in the stock a certain radial depth and a certain axial depth. All right, so an area. So it's taking out an area. It's more simply just state as this window right there. All right, that's the area that the end mill is removing. And then as the end mill moves over time, that's where we get our third dimension. And that is the rate of material removal over time. It's a volume. Okay. All right. So we go back to the notes now, and you will see where I've worked out two problems. So let's calculate the RPM and the feed rate for the following cuts. All right, and you can also do horsepower to spindle, which is real cool because it'll let you know if you're using the right material for a tool bit and if the machine has enough big enough electric motor. All right. All right. So the material is 6061 T6 aluminum. That's what you're going to be doing for your next project. That's the material you'll be using for your next project. The cutter is 3/4 inch tube fluid end mill. That is the tool you'll be using for your next project. All right. The radial depth of cut is 1/2 inch. And the actual depth of cut is 1/8 inch. All right. So using my little law right there, all right, the radius of a 3/4 inch diameter tool is 3/8. All right, so 0.375. In the problem here, I stated that the radial depth of cut is 1/2 inch. So 1/2 inch, 0.5, is greater than 3/8 inch, 0.375. So we have a slotting cut. Although we are still in the periphery of the part, it is considered a slotting cut. So we got to go to the slotting chart. So we go to the slotting chart right here. All right. Find my aluminum. Okay. And I zoom across. And now I'll see that the actual depth of cut is what is required when I am in a slotting cut. And my actual depth of cut is 0.125. So I read to the right, and I find my next column is my SFPM. I added the little S there for you, all right, feet per minute, okay, because inches per minute and feet per minute is, the acronym is two alike, differing by one letter only. So I added the S to make it easier for you to understand that if we're talking about surface feet per minute, which is V sub C, okay, it is 425. And then we read to the right further, and we can see that our with a slot 3/4 inch. Now notice we're on the periphery of the part. We're not completely in a slotting cut, but it's called the angle of engagement. The angle of engagement is the tool is great enough that accumulate enough volume of a chip load in the end mill to warrant a slower feed per tooth. All right, so you can see that we got 0.006, okay? Or I'm sorry, 0.008. I couldn't read that. All right, so 425 is my V sub C. My F sub T is 0.008. All right, now P is power factor. All right, and that's on the next page down that I haven't shown you yet. 0.4, I always assume 0.4, that's dull tool. All right, and then you just plug it into the formulas and work your numbers. All right, so I did one example for slotting and one example for peripheral. I hope you can understand this, and if not, when I see you here in the shop, I'll help you through the speeds and feeds. Okay, so there is only one little lab to do with calculating your own speed and feed, and that is going to be to calculate the speed and feed for the manual program that you have to program. All right. So you got a 3/4 inch cutter. Your material is going to be 6061 T6. You're only going down an actual depth of 1/4 inch. All right. And your R sub D, the R sub D is going to be something I'm going to let you think about for a while. R sub D is going to be when you go around the part, all right, you got to make 3 paths around the part to get that diamond made, all right? So actually, I'm not going to let you wait about it. I was just going to say you want to assume a slotting cut. You're going to be, some of you might be less than the radial depth of the cutter. Some of you might be more, depending upon the cutter diameter compensation values that you use to offset the color to the right. All right. So Those values we'll discuss when I see you in class, and maybe I'll do a future video on that as well. I do know the next video that I put up is going to be on the third uh, portion of how to write a program. I got to introduce you to the common blocks of programming. I like to teach programming in a method I call common block method. All right, that common block method is, I want you to remember blocks of codes together first. All right, you memorize them, because I can teach you 7 blocks of code that is on 95% of every program that you ever see. All right, so if you remember the orientation and the order of the codes within this block and what it does for a program, then we'll disseminate down into the individual G codes and learn each individual G codes for special situations. All right, talk to you soon. Thank you.